Wonder. Look closely at a plume of smoke, and you'll see pure chaos. To the human eye, gas is formless, unpredictable, and impossible to pin down. But if we step back and look at the container holding that gas, the chaos vanishes. We can't track 1 trillion individual molecules, but we can measure 3 exact properties of the group: the pressure pushing on the walls, the volume they occupy, and the temperature of the system. These 3 measurements are locked together by a strict mathematical relationship. Pressure times volume equals a constant, K, times temperature. Because of this rigid balance, you cannot alter one property without forcing a reaction in the others. Squeeze the gas to half its volume, and the pressure must double. That constant K remains steady for a sealed container, but it is entirely dependent on the actual amount of gas trapped inside. Pump more air into a tire, and the constant scales up accordingly. A gas appears chaotic only if you zoom in too far. On a human scale, billions of random collisions average out into a highly predictable mathematical dance. To make sense of this math, physicists rely on a theoretical model known as an ideal gas. In this framework, we treat the molecules as tiny particles, moving in straight lines, exerting absolutely no pulling or pushing forces on one another when they pass. Real molecules like oxygen and nitrogen do exert very weak forces on one another. Under high compression, those tiny attractions start to interfere, causing real gases to drift away from our neat equations. This chart plots the behavior of real gases at various temperatures against a drop in pressure. Notice how all the separate curves flatten out and merge into a single, perfectly horizontal line on the left side. As the pressure drops toward 0, the molecules are spread so far apart that their mutual forces completely vanish. The ideal gas acts as the natural baseline state every real gas eventually settles into once physical constraints like extreme pressure are removed. We can break our original equation open to reveal the actual molecules inside. That constant, K, can be expanded into 2 specific factors: the exact number of molecules present, N, multiplied by a new value called Kb. This is the Boltzmann constant. It represents the conversion factor between the average kinetic energy of individual molecules and the absolute temperature of the gas. This relationship explains the various gas laws discovered by early chemists over centuries. By holding any one variable constant, the math dictates how the remaining 2 must interact. This chart maps out Boyle's law. If you hold the temperature absolutely steady, the pressure of a gas becomes inversely proportional to its volume. Shrink the space, and the pressure climbs. And here we see Charles's law. This graph shows that if you hold the pressure constant, the volume of a gas expands in direct, linear proportion to its absolute temperature. These rules are not separate phenomena. They are individual glimpses of a single molecular reality. This brings us to a final, practical test. What happens to the math when we take 2 entirely different, non-reacting ideal gases and trap them inside the exact same container? Because ideal molecules are so far apart and exert no pull on one another, they are effectively blind to their neighbors. A molecule of oxygen will bounce around just as freely whether the vessel is filled with neon or completely empty. This yields Dalton's law of partial pressures. The total pressure on the walls of the tank is precisely the sum of the individual pressures each gas would exert if it were entirely alone. This aligns with Avogadro's hypothesis. Equal volumes of any gas at the exact same temperature and pressure contain the exact same number of molecules, regardless of their chemical identity or mass. The very feature that makes a gas seem completely chaotic, trillions of tiny particles moving at random, is exactly what creates the highly predictable additive laws that govern our macroscopic world.